Welcome back. Time to talk about more physics. This is video lecture 9.5, part 1, and we're going to talk about the reading in chapter 9, section 7, and we're going to focus now on elastic collisions. We explained what an elastic collision was in the previous lecture, and we're going to limit ourselves to a collision in one dimension, one axis, like an x-axis. Okay, so here is a picture of what we're generally assuming, what we're going to be focusing on. We have two colliding objects. Object 1, particle 1, object 2, particle 2. And the picture here, the diagram, shows them moving along an x-axis. And the convention that this book uses is to call one of the particles a projectile and the other particle the target. Those names are really not that important, but that's what this book uses. If one of the particles is initially at rest, we tend to call that one the target. So this book is going to say that if one of the particles is initially at rest, it's going to be particle 2. That's why they call particle 2 the target. Particle 1 has a mass m1, particle 2 has a mass m2, and the picture shows what's happening before the collision. The whole point here is that the objects are going to collide. So this picture here is, you might call it an initial picture. Before the collision. Okay? All right, now in this picture, particle 1 has an initial velocity, v1 initial. You can see the arrow showing that. And in this picture, particle 2 has an initial velocity, v2 initial, also denoted with an arrow. Although a lot of times in the situations we'll consider, v2 initial will equal 0. That means the target, particle 2, is just sitting there on the x-axis, and the projectile, particle 1, is going to come in and hit it. But that's our initial picture before the collision. We're not drawing a final picture. Final means after the collision, because the details of that picture will depend upon how the masses of the two particles compare, as we will learn. Okay? So we're only drawing an initial picture. We'll draw final pictures in problems when we know more about what the masses are. But here's the physics ideas we're going to use. We're assuming there is no net external force on the system. The system is the two objects. So we learned that if there's no net external force on a system, the linear momentum of that system is conserved. It cannot change. And since we're limited to an x-axis here, that means the change in the x momentum of the system must equal 0. And if the change in p sub x must equal 0, another way to say that is px initial must equal px final. We're going to use that fact to analyze this one-dimensional collision. So that's one constraint that has to be satisfied. But there's another constraint that has to be satisfied, because remember, if the collision is one of those special kinds called an elastic collision, that word elastic in physics, it has a specific meaning. It means the total kinetic energy of the system is the same before and after the collision. K total initial equals K total final. That's what elastic means. Okay? Remember, for all collisions in this chapter, all collisions, P initial equals P final. That's what I have up here. All collisions. P initial equals P final. But for the special collisions that are elastic, in addition, K initial equals K final, where it's the total kinetic energy of all the moving objects in the system before and the total kinetic energy of all the moving objects after. So let's write down equations that represent these two constraints on our system. First, P initial x must equal P final x. The total linear momentum must be the same before and after. Well, remember the simple formula for the momentum of a particle, mass times velocity. So we will write that down in symbols for both before and after the collision. All right, on the left, this is the before, the initial, before the collision. M1 times V initial 1. I'm not putting an arrow on the V's now because in one dimension we tend to just represent the direction of the vector with a plus sign if it's in plus x and a minus sign if it's in minus x, and that's what we'll do here. Okay? But please note that V1 initial means the velocity of particle 1 before the collision. And if that velocity is in the plus x direction, V1 initial is a positive number. If it happened to be in the negative x direction, then V1 initial would be a negative number. So M1 times V1 initial plus M2 times V2 initial. And of course, the V2 initial represents the velocity of particle 2 before the collision, with a plus sign if it's in the plus x direction, and a negative sign if it's in the negative x direction. Our drawing up above of the initial picture shows V2 initial in the negative x direction, so the V2 initial that would be substituted in this formula in this case would be a negative quantity. That's the left side, P initial. Now the right side of the equality is going to be representing P final. So the way we will write that in symbols is M1 times V1 final plus M2 times V2 final, where generally speaking, V1 final and V2 final are unknowns. The velocities of these objects after the collision are usually not known. And we have an equation, we'll call it equation 1, that comes from requiring the total momentum before and after the collision to be the same. But because it's an elastic collision, we have another constraint. The total kinetic energy must be the same before and after the collision. So let's write that in symbols. Okay? So first for the initial. 1/2 M1 V1 initial squared. That's the kinetic energy of particle 1 before the collision. That's what that represents. Plus 1/2 M2 V2 initial squared. That's the kinetic energy of particle 2 before the collision. Note these velocities are squared now, obviously. So whether the V1 initial or the V2 initial is a positive number or a negative number in the kinetic energy formula doesn't matter because the V's are squared. So that represents the K total initial, left side of the equal sign. On the right side, we'll have K total final. How will we write that in symbols? 1/2 M1 V1 final squared plus 1/2 M2 V2 final squared. And there we have equation 2. Same two unknowns, though, V1 final and V2 final. So we're considering these two equations as having two unknowns. The velocity of particle 1 after the collision, that's what V1 final means, and the velocity of particle 2 after the collision, V2 final. So, with two equations and two unknowns, algebraically, we should be able to solve. So we would solve equations 1 and 2 for V1 final and V2 final. Now that is, to a physicist, just algebra. Now, I'm not saying that algebra isn't kind of ugly. It's kind of ugly. You're welcome to go through it for yourself if you want. You won't gain any physics insight in doing that algebra. If you're skeptical and don't necessarily believe what I'm about to tell you, then by all means read chapter 9, section 7 to see the mathematical details. But I'm just going to tell you what you get when you do that just algebra, and solve equations 1 and 2, those two equations together as a system of equations for V1 final and V2 final. Okay, here we go. There they are. I'll put a box around them. Oh, put a red box. Because they are handy. I've numbered them equations 3 and 4. But I am just going to state them, right? I'm not going to derive them. The top one is the formula for V1 final in terms of M1, M2, V1 initial, V2 initial. The assumption is that in equation 3, those 4 things I just stated would be known in the problem. M1, M2, V1 initial, V2 initial. So equation 3 is the formula for V1 final. That is going to tell us what particle 1 is doing, i.e., what direction is it moving in and how fast after it collides with particle 2. That's equation 3. Equation 4 is going to tell me V2 final, the velocity of the second particle, the so-called target, after the collision. And again, it's in terms of M1, M2, V1 initial, and V2 initial. So I would plug in those known quantities into equation 4, and I would learn what V2 is doing after the collision. I would know what direction it's moving in, plus x or minus x, and how fast. That would be V2 final. Now we're going to do some practicing with these so we can start to get some insights from physics that's contained in these formulas. But I will give you just one more tip about using equations 3 and 4. This is one of the few occasions where I will just go to what I call canned equations. I called 3 and 4 canned equations. Specialized, only valid in a very limited situation, and therefore not that important in the big picture. But if I am in a situation, limited though it may be, where equations 3 and 4 are correct and appropriate, then I will go straight to them and use them, as long as I am confident that they are valid. So, I will use equations 3 and 4 directly whenever solving a problem involving a one-dimensional elastic collision. If I know that's what I have happening, a one-dimensional elastic collision, I'm not going to rederive equations 3 and 4 from scratch. I'm going to go right to 3 and 4 and use them. Okay? And I'm not normally a big fan of going to these specialized canned equations, but these are messy enough. If I know they're valid, then I'll go right to them. And you are allowed to do the same. Okay, so let's practice. Now remember, an elastic collision, as I said in the previous video lecture, is rather rare. And you need to have objects colliding that tend to not deform. So they tend to be pretty rigid, like pool balls, or the little steel spheres in Newton's cradle. Remember I showed you Newton's cradle? Okay? They tend to be non-deformable things, right? And they tend to be pretty quick collisions, like the steel spheres in Newton's cradle, or pool balls. But generally speaking, how will you know in solving a Wiley Plus homework problem if the collision that you have to deal with is elastic, the special kind elastic? It's going to tell you almost always. It's just going to plain tell you in the wording of the problem that it's an elastic collision. So let's go right to some practice with one-dimensional elastic collision. Okay? Okay. Here's the scenario. Well, the figure shows a snapshot of actually 2 blocks along a horizontal x-axis that's a frictionless floor. Okay? And block 1 is sliding along this frictionless floor, this x-axis, and it's about to undergo see, it tells me, an elastic collision with block 2. So this is the initial picture that it's drawn for me. Initial here means before the collision. And it tells me that before the collision, block 2 is stationary. Well, I know what stationary means. It means at rest. So we have a situation where particle 2 is initially not moving. That's going to make things a little bit easier to deal with. That means then V2 initial, the velocity of particle 2 before the collision, is 0. And everywhere where that symbol, V2 initial, appears in equations 3 and 4, which are going to be valid here, wherever V2 initial is, we get to put in 0. So we might as well go right up right now to equations 3 and 4, and everywhere where you see V2 initial, right there and right there, put in 0. That's going to simplify equations 3 and 4 considerably. All right, now there's more to what I'm told. The figure also shows 3 possible positions of the center of mass, COM, of the 2-block system at the time of the snapshot. All right, those dots there, A, B, and C, are not particles. They're possible locations of the center of mass of the 2-block system in this snapshot. Note, point B of the 3, A, B, and C there, is halfway between the centers of the 2 blocks. All right, here we go. Here come some questions that it's going to allow us to practice with equations 3 and 4. Question A. What happens to block 1 after the collision if the center of mass is at point A in our snapshot? This is one of those ones that sometimes people see that and they go, I'm not even sure what I'm supposed to do here. But we're actually being told a good bit of information. Let's think about it. Our snapshot shows a moment in time before the collision. Block 1 is to the left, block 2 is to the right. Block 2 is initially at rest, block 1 is moving to the right. We're assuming, by the way, that to the right is the plus x direction. So V1 initial is a positive number and V2 initial is 0. And they're going to undergo a one-dimensional elastic collision. And apparently, when we took the snapshot, the center of mass of the 2-block system is at the point labeled A. And remember, the point labeled B is exactly midway between the blocks. That means the point labeled A is closer to block 1 than it is to block 2. That tells you something. That's a clue. It tells you something about the relative masses of the blocks. What does it tell you? Did you say that block 1 must have more mass than block 2? Yes? Because remember, the center of mass is biased towards the more massive object. If the center of mass is at point A, and A is closer to 1 than 2, then 1 must have more mass than 2. That's very important in understanding what's going to happen in this collision. That means the projectile, 1, that's coming in, has more mass than the target, 2, which is sitting at rest. That's enough for me to predict what block 1 is going to do after the collision. Because what they're asking me is, what can we say about V1 final, the velocity of block 1 after the collision? Well, let's use equation 3. That's the one that tells us V1 final. Let's write it down. V1 final equals, use equation 3. And remember, V2 initial is 0, so that whole complicated stuff in the second term of equation 3 doesn't even enter in. And the formula for V1 final is merely this. M1 minus M2, be careful not to reverse the order of those, over M1 plus M2, you're free to reverse the order of those, times V1 initial. Watch all those symbols very carefully. We have to apply this equation correctly, and that's the formula. Now, again, what can you tell me about V1 final if M1 is bigger than M2? Look right at that formula I just wrote. Look specifically at the numerator inside that complicated-looking fraction. If M1's bigger than M2, and you take M1 minus M2, you're still going to have a positive number, aren't you? And of course, M1 plus M2 is a positive number. So my point is, M1 minus M2 is greater than 0. That's that numerator that determines the sign, S-I-G-N, of V1 final. So V1 final will be a positive number. That tells me the direction that particle 1 is moving after the collision. It's moving in the plus x direction. It's moving in the same direction it was originally. Yes? So block 1 keeps moving in plus x direction after the collision, right? I can deduce that. I'm not plugging in any numbers here. I'm just telling you basic things. Like I can tell you, I know for sure in this situation that after the collision, block 1 will be continuing to move in the plus x direction. Now, of course, block 2 has to be moving afterwards as well, but it doesn't ask us about that, does it? So I won't worry about block 2 right now. But I can tell you definitively that block 1 will continue to move in the plus x direction. I can even tell you a little bit more than that. I can tell you that V1 final will be less than V1 initial. You see how I can tell that? Because to get V1 final, I'm going to take V1 initial and multiply it by a fraction. That's the quantity in the parentheses. And I know that fraction is less than 1. Yes? Because in that fraction, the numerator is M1 minus M2, and the denominator is M1 plus M2. The numerator is smaller than the denominator. So I know that V1 final is less than V1 initial. So the block will continue to move in the plus x direction. It will continue to move to the right, but it will be going slower than it was before the collision. Well, it did impart some momentum to the other block. Okay, so that's my description of what's happening to block 1 after the collision, given that the center of mass is at the point labeled A before the collision. Okay? That's all. It's a kind of a conceptual exercise here. Let's go on to B. What happens to block 1 after the collision if the center of mass is at point A? All right. So now the center of mass in this snapshot is right there. Point B. Remember, point B is exactly midway between the two blocks in the snapshot. What can you tell me about the masses of the two blocks in that situation? Did you say that the masses must be equal? Yes? If the center of mass is exactly midway between them, they must have equal mass. All right, let's figure out what block 1 does after the collision in that case. Okay, so what about V1 final? Well, again, use equation 3. Let me bring it back into view so you can see it. Look at equation 3 for V1 final. Actually, you can see it right if I leave it right here. Right? There's the formula for V1 final. So use it. Tell me what V1 final is going to be, the velocity of block 1 after the collision, if the two masses are equal. Did you say V1 final equals 0? Bing! Right? Because in that formula, if the m1 and the m2 are equal, look what you have in the numerator of that fraction, m1 minus m2, 0. Block 1 stops as a result of the collision. Yes? Block 1 is at rest after the collision. Let's see what block 2 does. What about block 2 after the collision? Use equation 4. Right? Okay, I'll bring that one back into view so that we can see it. Equation 4, I want now V2 final. Remembering V2 initial is 0, there it is. I'm going to take this back up here and I'm going to write down, oops, pardon me. I'm going to write down the formula for V2 final, i.e. equation 4. V2 final equals, so we get another fraction, times V1 initial, yes, V1 initial. We have 2m1 in the numerator, and the total mass m1 plus m2 in the denominator. Let's see what we get for V2 final. It's clearly going to have to be moving, right? Block 1 stops. So block 1, block 2 is initially at rest, block 1 is moving, comes in, collide. Elastic collision, equal masses, block 1 stops. Block 2 has to be going on in the plus x direction. Let's see what we get. Now remember, the masses are equal. So let's say m1 and m2 are both just m. Then I'll have for my fraction here 2m upstairs, but look what I'll have downstairs. M plus another m. Well, that's just another factor of 2m. So look what the fraction is, 2m over 2m, which is 1. So V2 final equals V1 initial. So V2 moves off with the same velocity, block 2 moves off with the same velocity that block 1 had before. In fact, we say that the particles, the blocks, have exchanged velocities. As a result of the elastic collision. Yes? Because block 2 was initially at rest, block 1 was coming in with a certain velocity, V1 initial. They collide. One-dimensional elastic collision. Block 1 is now at rest, and block 2 moves off with a velocity equal to what block 1 had initially. So in a one-dimensional elastic collision, when the particles have equal mass, they exchange velocities. Okay? V2 final is equal to V1 initial. And V1 final is equal to V2 initial, right? Goes for both. Let me show you a video of that. Professor Storms and I, one of the other physics professors in the department, made a video using our Airtable in the lab with 2 of our pucks, like you did experiment 5 with on the Airtable. Except these were slightly different than the ones you used. These have magnets in them. And they're set up to have reverse polarities, so when the magnets get close to each other, there's a magnetic repulsion. And that's going to act like a kind of a collision between them, and it's going to act like an elastic collision. So we tried our best to make it one-dimensional, so that once, and we're going to have one of them initially at rest, and the other one comes in. We tried to get exactly a head-on collision. Takes a bit of practice. And the pucks have approximately equal masses. And so you should see that approximately block 1 stops, and block 2 moves off with the velocity that block 1 had. Okay, all right, now, give me just a second to get this set up. So now you see the 2 pucks. Yeah, I know, don't do that to me, Wiley Plus. Hold on here, folks. Bear with me a minute. Okay. You see the 2 pucks. I'm going to be pushing particle 1. Particle 2 is at rest. I tried to get them head on so that we have roughly a one-dimensional elastic collision, and it's in slow motion. Well, I thought it was, but I guess it wasn't. Okay, did you see it? Let me show it again. Here we go. That was pretty good, right? That one, the first one basically stopped, and the second one went right off in the same direction as the first. Okay, so there is an example of the exchanging of velocities. Okay, one-dimensional elastic collision, equal masses. Now, let's go on. There's a part C. Let me get that back into view, the question. What happens to block 1 after the collision if the center of mass is at point C in the snapshot? So, get rid of it there. Now the center of mass is there in this snapshot before the collision. What's going to happen to block 1 after the collision now? So tell me, what can you tell me about the relative masses of the blocks, in this case, if the center of mass is at point C? Did you say that in this case, it's M2 that is bigger than M1? Or to say it another way, M1 is smaller than M2. Right? Because now the center of mass is at point C, which is closer to block 2. The center of mass is biased towards where more of the mass is, so it must be the case that M2 is bigger than M1. So now what can I say in this case about V1 final? Well, use equation 3 again. Let me bring it back into view here. It's that equation circled in yellow. What can you tell me about V1 final if M1 is less than M2? Look at the equation I've circled in yellow. All right, did you say that what you can tell me is that V1 final is less than 0? It's going to be a negative number because we have to do M1 minus M2, and M1 is smaller than M2 in the numerator of that fraction. So I know that I'm going to be taking a negative quantity, negative number, times V1 initial. V1 initial was positive. So V1 final is negative. Well, what is that telling me? That tells me that block 1 rebounds. Yes, it goes back and moves in the negative x direction. Okay? So now, if block 1 has less mass than block 2, block 1 comes in, block 2 is at rest, block 1 bounces back and goes backwards. But block 2 must, by the way, go on in the forward direction. We didn't look at equation 4, but you can convince yourself that's true from equation 4. But what I do know from equation 3 is that the formula gives me a negative number for V1 final when M1 is less than M2. So I know that block 1 rebounds and goes back in the negative x direction whenever block 1 has less mass than block 2. Okay? So these are things I can just figure out by looking at equations, thinking about equations 3 and 4. I want to look at one more application of equations 3 and 4. I want to consider really what is a special case of question A. Okay, here's what I want to ask. What happens if M1, mass of the incoming particle, particle 1, it's not just bigger than M2, it's much bigger than M2. It's not just greater than M2, it's much greater than M2. The way we denote that in physics, how do you like that? Two greater than signs. So I want M1 to be much greater than M2. What happens in that case? Well, it's got to be true that M1 then continues moving forward in the plus x direction. You can look at equation 3 and convince yourself that would be true. What I'm really interested in is block 2. Block 2 is about to get pounded by the first block, right? First block has a lot of mass compared to the second one. All right? So that's like hitting a little Vespa with a Mack truck. I want to know what the Vespa's going to do, okay? All right. I want to see what V2 final is. Remember, V2 initial is 0. Well, the formula for V2 final is right up here in front of us, right there. Go ahead and circle it in yellow. V2 final. I want to simplify that. I want to say, well, how does that simplify, reduce, in the limit where M1 is much larger than M2? So a physicist is confronted with a situation like that and says, well, I can take that formula and I can simplify it. That is to say, in the denominator, where I have M1 plus M2, M2 then is a small number added on to the big number. Focus on the big number, right? 1,000 plus 1. Yes, technically it's 1,001. But at least to get a sense of what it's going to be, it's good enough to say it's 1,000. So I'm going to replace M1 plus M2 with just M1 in the V2 final formula. It's technically an approximation, but if M1 is much, much greater than M2, it's a very good one. Then it simplifies the formula, because now I'm left with an M1 upstairs and downstairs, and it just cancels. And I have, technically it's approximately, 2 V1 initial. Positive, of course. So particle 2 goes in the positive direction twice as fast as particle 1. What we have, because of the factor of 2, is called a speed amplifier. You can shoot the target, particle 2, out twice as fast as the first one came in. And therefore, you can get pretty fast-moving particle coming out. Let me show you a Wiley Plus video of a professor doing that. The professor is going to hold a basketball and right above it a tennis ball and drop them onto a tabletop. So the basketball lower than the tennis ball. So the basketball hit the tabletop first, bounce and come up. That will then hit the tennis ball, which is still going down. We'll approximate that as a one-dimensional elastic collision with a significant mass difference. Basketball has quite a bit more mass than a tennis ball, and so the tennis ball should shoot up quite a bit faster than the basketball. Okay, hopefully I haven't lost. There we are, the double ball drop. Let me run it. Give it a second, it's going to show. What we have here is a basketball, tennis ball, ping pong. Now, if I drop the basketball, do a step, not down from high, so there's a last equation between the basketball and the tabletop, of course. However, it's going to lose a little bit, so it's not going to be high. Here's our tennis ball, same thing, and here's our ping pong ball. However, if you combine the two and make a system where I drop this ball on top of the other ball so that the basketball first hits, then comes back up, although the tennis ball is dropped at 6 height, it is certainly a height much higher than we're used to. Why is that? Try one more time. Again. Okay, so that showed, I think, pretty well this phenomenon I'm talking about of a speed amplifier, when you collide a very massive object with a much lighter object. You can amplify that even more by having a chain of objects from most massive, successively less mass to very light, and have successive collisions, always with the more massive hitting the less massive, and the last one, the lightest particle, comes flying out amazingly fast. Okay, so we will be talking in the class about one-dimensional elastic collisions, so we will be practicing more with this, but that's all for now for this video.